Hey, I was thinking about something today.
What were you thinking about?
I was thinking about the Nobel Prize in 2011. Do you know what it was?
Okay.
Yeah.
No, no.
It was the discovery of an accelerating expansion of the universe.
Okay.
Pretty neat.
And what is the acceleration of the expansion of the universe?
It means the universe is expanding, and not only is it expanding, it's getting faster in time. Something you would not expect, given that the dominant force over large distances in the universe is gravity. You would think it would contract, but no, it's expanding and faster and
Wait,
faster.
I'm out now. I'm actually confused. Now that you said that, it says the expansion of the universe is accelerating through time, getting faster and faster through time. But isn't time part of the universe? How we got
Correct.
this independent parameter? I think there's a
What?
way to do this.
What? What?
So, like, time is not outside the universe. So, how is it expanding through time if time is part of the universe? Do you know what I'm saying? Like, I can't have this.
I hate this. I hate this right now. I just want to share a cool thing. Okay,
Okay.
so it's if time is constant, the universe is getting bigger and bigger and bigger,
Mm-hmm.
and so and not only is it bigger, 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 it's getting bigger and bigger and bigger, faster, faster, faster.
That makes
So
sense.
not only is the size of the universe like a constant gas pedal, it's getting faster, faster, faster. So it's expanding through time, across time,
Mm-hmm.
adjacent to time. What time's involved? What are we doing?
Well, I mean, my picture is the universe is expanding, and I have a
Mm-hmm.
picture of the universe expanding through time. But my time axis is outside of the universe. So there must be a way to define it. I'm overthinking it.
You're overthinking it. Let's picture will help.
Okay.
All right. So here we have the Big Bang.
Yep.
And so then the universe rapidly expanded and got to some size. And then the universe was still growing, but not very fast. And at some point in time, this growth, the size of the universe gets faster, bigger, but faster and faster and faster. So note that this curvature is concave, concave. It's getting wider faster. So this is the time where we say the acceleration is increasing. And here in green, if you were to look at the size of the universe, you would expect that gravity would pull everything in. But we see from the data that the universe is getting larger, 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 faster, faster, and faster, which means that something is counteracting gravity, something is pushing out. Is the consequence of this accelerating universe is the supposition of dark energy. It's there somewhere. It must be because we're not contracting, but we don't know what it is.
And then dark energy is the thing in Einstein's equations called like the cosmological constant. This is right at the edge of my knowledge here.
It's the fudge
Where
factor.
the
It's the big old capital lambda where he's like, this is the greatest mistake I've ever made. I don't know how to solve this, but this is the only way for the equation to work. Turns out it was this.
I think he wanted the universe to be
Static.
forever static, so he
That's right.
needed a counteracting force to gravity, which would be an expansive force.
Mm-hmm.
So he included it, and he didn't like it at the end of the day.
He called it his fudge factor.
And I believe in Newton's equations, we have the 1 over r squared. I believe you can actually add a cosmological constant, like it's valid. It doesn't change anything. And that's why he did it, because it's valid there. I don't know why Newton didn't include it. But either way, apparently
know.
it's there.
Mm-hmm.
So weird. I guess if it's mostly an experimental statement at this point, is that right? Like we
What do you mean?
measured that the universe is expanding and that expansion is accelerating,
Yep.
but we don't know what dark energy is exactly. Is that
Oh,
right?
no, exactly right. Dark energy is the supposed solution to make the measurements make sense. So we measure that the universe is expanding. Not only that, it's getting faster and faster and faster. And so but the only force that we should expect on the cosmological scale is gravity, which is a contractory force. It's the force that pulls things in. And so, but we see from the data that something is stronger than that. Something's pushing things out. And so then we suppose dark energy to fill in that void.
And I guess that's different than dark matter, which is another one of these darkies.
Mm-hmm.
That is important for some other reason. We also haven't detected that either.
Correct. We have detected dark matter from the rotation curve of the galaxies. So if you look at galaxies and how they spin, if you have a central body in the middle, then you would expect the gravitational force to get weaker as you get out, and so things should slow down. But instead, what you see is that things on the outside of galaxies are surprisingly fast, which suggests there's much more mass in the middle of galaxies than we expected, but that mass isn't generating light. But it's there. We see the mass evidence of it. It must be dark matter.
Yeah, and I guess we don't want to throw away the 1 over r squared rule of Newton's laws and Einstein's gravity. So there must be missing mass. I guess some people have worked on like alternative gravitational theories, but none of them have panned out yet.
Right.
So we're stuck with this like there's missing mass. And then for the expansion of the universe, it's still like there's missing energy.
But we don't see it. It's not emitting light. It's dark in the sky. Dark energy.
Yeah.
So how do we determine this? How do we determine that things are like what is the measurement in which we see that things are expanding faster than they used to? And I think that if I'm correct here, it's looking back. Here's the cosmic microwave background. This is from the Wilkinson microscope anisotropy probe. So isotropy is iso, so the same, and then tropy, that's a word. And so this looks at the evenness of the galaxy. How smooth is it? And so while we see some reds and blues, that's like the largest variations. So, but that's an arbitrary color scale. You set the rainbow scale to whatever it is. So let's say it's like if I had something that was an inch tall and something that was a foot tall, the foot tall is red, the inch is blue. And if I had something that was an inch tall versus 10,000 feet tall, like I can still set the color scale to be red and blue. So even though this looks like it's hot spots and cold spots, it's actually very smooth. And so it's very smooth, suggests that the Earth, that the universe came from a time in which the universe was super small, in which photons could cross that distance, and then it exchange energy, equilibrated temperature. So this is the Wilkinson map and anisotropy probe, WMAP. It's the cosmic microwave background, and it's when we look everywhere in the sky, the universe is about the same temperature, which you wouldn't expect because the universe is so big, you can't get a photon from one side to the other to tell the left side of the universe, like, hey, I'm hot over here. Let me give you some energy to the cold spot. Like, the universe is too big for that. Okay. So now we've said there's a Big Bang. This discussion got so big so fast.
Mm-hmm.
Okay.
So from what I understand for the cosmic microwave background, it's somehow this is the big evidence for that rapid expansion of the universe early in time.
Yep.
Where things were coupled early, and then it allowed the universe for some reason expanded quite rapidly, and so it was the temperature distribution is the same everywhere.
Exactly.
Although the anisotropy of it is important somehow, and they go the the weird thing about that is they like go to like the 1,000th spherical harmonic when they measure it, and it's like the data for the expansion of the universe matches it. It's super weird. I don't understand it. But apparently this is open and shut case for rapid expansion. What is the right word? Inflation. That's what they call it.
Yeah.
Inflation.
Yep. This period in the very beginning of the universe where the universe, like Big Bang, a little bit of growth, and then gigantic real quick.
I think that's consensus, but I don't know if everybody's on board with inflation. But I don't know enough to poke holes.
I don't either. Okay, so this inflation period is right down there, this tiny little bit. It's real quick, real small, very at the beginning. And then here we're relic radiation, cosmic microwave background, CMB. That's the picture we saw up above for the WMAP. And then we're off to the races. We're off to the races of the expansion of the universe. Just after the Big Bang, we're coasting. But there was a coasting period, and then it gets faster, faster, faster. And so the question I have to you is, how do we know that it gets faster, faster, faster?
I mean, I think that's a data-driven thing, right? That
Exactly right.
we've somehow established we know the distances to all these things in the universe, and when we look close, things are moving away from us pretty slowly, and as we look far away, things are moving away from us pretty quickly.
Right.
And we can create this curve of how far away something is versus how much is moving, how fast it's moving away from us. We get this curve, and we see it's not a straight line. It's actually concave up. It must be.
Yep. Going faster, faster. Yep. So I'll read the same thing that you said, but read it from Wikipedia. Observations show that the expansion of the universe is accelerating, such that the velocity at which distant galaxy recedes from the observer is continuously increasing with time. So as things move away from us, they're actually getting faster, faster, faster. So the tricky thing there is, how do you know how fast things are when they're far away? Like, if I'm here with my human eyes and I see a dog running away from me, I can just see it, right? But imagine your one eye is closed, you see the dog running away, and you're not allowed to do this bob and weave stuff. Like how can you see how far away things are? That's our situation. We're here on Earth. How do we don't have like a second Earth that we can work with. So how do we see things that are far away?
So my understanding of this is that the velocity part of the measurement is actually the easy one.
That's right.
Because we can look at the spectrum of all the objects far away and see if it's redshifted or blue shifted. And redshift would be something moving away from us, meaning as the light is emitted from the distant object, the light is expanded into lower energies. That's a redshift. And if it's moving towards us, light is compressed into higher energies. And we see this redshift as things get farther and farther away. And we can just look at the spectrum and see like specific characteristic lines. I think the hydrogen lines are the ones we use.
Yep.
And we can see where they're shifted relative to us. But
Exactly
the difficult
right.
one is the distance measurement, right?
The distance. But let's slow it down there a little bit. That's pretty fast what we just said. Maybe if you've taken astronomy before, that you'd follow that. So it's the same effect as when you hear sirens driving towards you, and they get higher and higher frequency, higher and higher pitch, and then when they go away from you, they get lower and lower. So just like ice cream trucks, you and it's like faster, faster, faster. But then as it goes away, it goes like it's like that broken record thing.
It's like
Super
a Lamborghini ice cream truck here.
Yeah. Ice cream trucks used to rip around my house. So the same thing that happens with sound happens with light. And so here, if we have a rainbow with some lines that are missing because they've been absorbed out by a gas, if this gas is moving away from us, then these lines shift towards the red. And if things are that's a redshift. Yeah. So exactly as you said, that it said finding the spectrum of light that's emitted by an object is actually very easy. You just look at it, spectralize it, decompose the light from whatever it is to break it apart into its colors.